All right, hello everybody. So this is just a short video illustrating what it looks like if you construct a binary heap sort of step by step. We're going to do this in two different ways. We're going to just insert each element one at a time, and then we'll also try using the build heap algorithm, which is kind of like a sort of magical kind of things here, right? All right, here we go. So we're going to insert these values in this order into a binary max heap. Of course, the first value is easy, right? 12 just becomes the root there. Then 56 is placed in the next available spot. Remember that this tree has to be complete, so I'm going to fill it in top to bottom, left to right, like that. I put 56 in the next available spot, but that would violate the heap order, right? I'm only allowed to put things underneath 12 that are less than 12. We're going to fix up, which will swap 56 and 12. So this is what the tree looks like after inserting 56. Then I insert 23 in the next available spot here. 23 is less than 56. Right? This does not violate heap order property, so 23 can stay there. 78 goes in the next available spot, which is starting a new row down here. 78 is going to violate the heap order property, right? Only things that are less than 12 are allowed down here. So we're going to swap 78 up. 78 here still violates the heap order property. Only things here are allowed that are less than 56. We're going to swap 78 again, leaving 78 as the root. So this is the state of the tree after inserting 78. 15, the next value is going to go in the next available spot. And 15 is less than 56, so it's allowed to stay there. So I don't have to do that. 67 goes in the next available spot. But 67 here violates the heap order property, right? It's not less than 23. We're going to swap it with 23. When 67 is here, it is less than 78. So 67 is allowed to stay there. It doesn't need to continue moving up there. And then finally, 45 goes here. 45 is less than 67. So it doesn't need to move. So that's what the, this is what the tree looks like when we're like this, right? Is we're just sort of finished. Okay. All right, now we're going to do the build heap algorithm. So the build heap algorithm starts by just dumping these values into the heap array here. That just means we're going to fill in the tree top to bottom, left to right here. So 12, 56, 73, 78, 15, 67, 45. If you drew out the heap array here, right, that's 7 things. This. I made the slideshow right, and just sort of start index 1, 2, 3, 7 like that. It would just go 12, 56, 23, 78, 15, and 45. And this is not a valid binary heap, right? It is a complete tree, that is true, but it violates the heap order property like all over the place, right? So we have here 78 is not less than 56, 56 is less than 12, 23 is not less than 12, 5 is not less than 3, 7 is not less than 23. So clearly we can't leave it alone like this. So what we're going to do is we're going to start at the end of the array, work our way backwards towards the beginning, doing fix down operation. We're going to perform fix downs, basically starting here and working backwards like that. Now, of course, when we do a fix downs on the leaves, that's not going to do anything. They don't have any children, so like nothing sort of happens here. In fact, we probably wouldn't actually do fix downs on these here. We would start our fix down process on the first node that has a child. So we would actually probably start it at 23. When we do a fix down at 23, we're going to swap 23 with our larger child, which is 7. So 67 moves up and 23 moves down. So the thing to notice, right, is this is now a valid max heap, right? 67 is larger than 23 and 45 here. If you look at just one of these leaves by itself, 78 is a valid max heap. 15 is a valid max heap. So the property of fix down is if you do a fix down and both of your children are already valid max heaps, then fix down will turn the whole thing into a valid max. Like watch it happen here at 56, right? So is this a valid max heap by itself? Yes. Is this a valid max heap happen by itself there? If I do a fix down with 56, that's going to swap with 78. So now this entire section is a valid max heap. Now I already said that this entire section is a valid heap. So the next thing we're going to do is going to do a fix down up here, which will have the effect of turning the entire tree into a valid max heap. So we do a fix down from 12, that's going to swap with 78. Then 12 needs to continue to move down because it is smaller than 56. So we move down there, and we're done like that, right? So you'll notice that we did 4 fix downs down here that basically did nothing. Then we did 2 fix downs that could potentially move 1 level, and then we did 1 fix down that had to move 2 levels there like that. So if you add up the sort of total amount of work that all those fixed downs do, you get a total of O of n for the whole thing there like that. In this case, we ended up with the same tree. Like if you compare this one to the tree that the inserts gave us, they're identical. That's not a guarantee. Build heap doesn't necessarily give you the same heap as repeated inserts there. It's just pure chance that, that they did in this case here. The insert method is going to take n log n time, whereas build heap is faster. It's going to run in O of n. But anyway, that's just a couple examples of what it looks like to build a heap there. See you next time, everybody.